Okay, so we're into solutions. Hopefully you were able to do the Nearpod last time. That should have helped you a little bit understand what we're going on today. If you guys want to close the door, that'll stop the northern wind from coming into our classroom. That tends to go really good when the snowing outside. All right, so last time you should have learned about colloids and solutions and suspensions by doing the Nearpod. If you didn't, we're going to go over them a little today, but we're going to go fast. In order to get through everything that we need to in this little bit of time, because by next Friday we're taking a test, I'm going to be pushing you. And the way that the lab is set up, we'll be doing a little bit of lab starting next time every day. Okay? So, solution, solvation. No, it's not salvation. It's solvation. So it's not religious. Suspensions tend to affect colloids, and you did this solutions, colloids, and suspension activity you were supposed to. I heard a lot of you didn't. It'll take us 5 minutes back in lab. We'll do it real quick, and then you can turn it in. Okay? You should be working on your Learn Smarts and your homework. I'm hoping you're almost done with them. If you aren't, you need to get going on them, because this is a real short unit. Okay, today we're going to talk about pure substances, mixtures, equivalents, which is something that you need to make sure you get in your head, solubility rules, and at the very end I'm going to bring in molarity, molality, because you need them for the pre-lab, but we'll go into them more in depth later. Okay, so here we go. When we talk about mixtures, we're talking about pure substances versus mixtures. Pure substances, there's very few things that are pure substances. This is elements by themselves, compounds, ionic compounds. But most of the things that we come in contact in the real world are mixtures. That's where they're made up of two or more things. We have heterogeneous mixtures and homogeneous mixtures. When we go back to lab, when we're doing lab, you'll be able to see heterogeneous mixtures are things that don't mix evenly. They don't mix the same all the way throughout. So it would be like having a chocolate chip cookie versus a sugar cookie without frosting. So the sugar cookie would be the same throughout, the chocolate chip would have the chocolate chips in there. So heterogeneous, different uniformity. Homogeneous, same throughout. Okay, so we're taking notes. We got it? I don't want to go too fast, but I want you to make sure you got the stuff. We ready to roll, Paige, or need a few more seconds? Okay, so when we're looking at solutions, states of solutions, physical states, we have a solution is a homogeneous mixture. So when I say solution, it's homogeneous throughout. The particles are very, very small. Okay, it's usually transparent. You can see through it. A solution consists of two parts, a solute and a solvent. The solute is what you're dissolving. The solvent is what's doing the dissolving. Usually when we talk about a solution, we're talking about an aqueous solution for the most part. But there are solutions that are not aqueous, meaning not with water. Water solutions have to be polar in order to become a solution. So whatever my solute is has to be polar to be able to be dissolved and make a solution. So instead of saying the thing that's dissolved, oftentimes the solute is considered the thing that's the lesser amount, and the solvent the thing that's the greater amount. You'll see a couple of things here coming up. We okay to go forward? A few more seconds. I'm trying to force myself to stay away from the board. Okay, good to go? No, I told him to go. Jace, are you paying attention with us? No. Okay. Good? All right. Okay, so this is just, again, solute versus solvent. When we look at a solute, that's like salt. And in a salt crystal, you have positive, negative, like this, where sodium here is the white, chlorine's the green. And we have water, and water is a slightly polar molecule. Remember, we had a negative side and a positive side. And when we have a solvation, then we get what's called hydrated ions down here. You'll notice that the oxygen on the water is attracted to the sodium ions because that side of the water molecule is negative. And the positive side of the water molecule, which is a hydrogen, is attracted to the chlorine ion because it's negative. And that's how it's pulled into solution or solvated. Okay? So we have hydration. And hydration is putting water molecules around each of those ions. This is actually part of the MCAT. So if you learn this, then you learn something that is going to be on the NCAT. Hydrated ion can be an anion or a cation, but it's just how water is arranged around it or surrounding it. Okay? And it's all based on polarity. So a hydrated ion could be a cation or an anion with water surrounding it. I tried to draw it as simple as I could for you. And you could even just draw one water molecule or two around it so you could see what they're going to do. Remember, as you're looking at anions and cations, anions are usually larger because they've gained an electron and they don't have as many positive protons in the center holding those electrons close to them. And a cation is usually smaller because it's lost an electron, has less electrons to hold close to it, so they hold them a little bit closer. Okay? And we're going to be talking about size and how they filter and stuff like that in a minute. We good to go on this one? Remember, you have colored pencils you can use if you want them. Okay. So let's look at some examples. Let's talk about these examples. As we're looking at these things, if we look at foggy air, so would that be a solution or a non-solution? Non-solution. It's actually a colloid. Okay? A colloid has a little bit bigger particles than a solution. What about tears? That would be a solution. Good. And what about maple syrup? Depends on the maple syrup. You'll notice there's a varying degree of color, and depending on the size of the particles inside the maple syrup, it can be a solution or a colloid, but more often it's a colloid. Okay, we'll talk about those in a minute. What about dental filling? Non-solution. Okay, what about milk? Actually colloid. Okay, what about creamy hand lotion? That would be a colloid or a non-solution. What about saline solution? It says solution. It is a solution. Okay, so let's go forward. What is a colloid? I use that word a lot. A colloid is a mixture, a homogeneous mixture that has particles larger, just barely larger than a solution. But they're large enough that they catch and reflect light. Okay, so how many of you have driven in fog before? Okay, when you turn on your headlights, what happens? The whole area just lights up, right? And it makes it really hard to see. But if you have fog lights, which are pointed down and a darker color, you're actually able to see, right? But if you use that bright white light, white light reflects off all those particles in the air and makes everything just illuminate. Okay? So colloids are particles that are small enough to reflect, that are small enough to stay in solution, but big enough to reflect light. Okay? It gave you some ideas here like milk. Another one that's not up there would be like Jell-O. Jell-O is a colloid. Okay, so they do not separate in layers, but the particles are bigger than a true solution. You can't filter it out, so you can't put it through a filter and have the particles come out because they're too small. They will scatter light because they're big enough. The difference between colloids and suspensions. Both colloids and suspensions will scatter light, but with a suspension, it will separate out and you'll get those layers again. Okay? A colloid will not. So when we go back to lab, those of you that, did anybody do the lab last time? There's a couple of you. Okay, so when you did that and you saw the milk was a colloid and it had a Tyndall effect. But when you did the dirt and water, that gave you the Tyndall effect, but it settled out after time, and because of that was a suspension. Okay, the same thing with oil. If you shook it up right before you shined the flashlight through it, it gave you the Tyndall effect. You let it sit, it separated into layers. that's a suspension. Okay? Anybody have a question between what a solution, colloid, and suspension is? Okay. So as we look at it, I'm going to bring this next part up. We can measure it in centimeters, but sometimes it's easier to see it in nanometers, but I've left the centimeters up there. Underneath 10 to the minus 10 centimeters, which is less than 1 nanometer across, that is considered a true solution. So as I'm looking at a colloid, I can actually see a colloid if I've got a good microscope. I can see the particles of colloid. They're a little bigger. Okay? They're between 1 nanometer and 1 micrometer. But if I get too big with a suspension, I can see it with a really low-powered microscope, or even sometimes with bare naked eye, like in that dirt solution. And I'm going to get a settling out. I can filter it. The other two I can't filter. Now, it's set up on the colloid by a common filtration method. There are filtration methods that we can get it to separate, but they're very extensive. You have to use column filtration as one of the possible ways to filter it. So that fancy little U-looking thing is a micrometer. So you can see they're really, really, really small. A 100 times smaller than a millimeter. Okay, we okay to go forward? No. Good? Okay. All right, so with this, now we need to talk about electrolytes and non-electrolytes. Now this is a nursing chemist, basically, or pre-engineering. And with electrolytes, we worry about can it conduct electricity. So if my salt separates into sodium ions and chlorine ions, sodium ions are positive, chlorine ions are negative, I can conduct electricity through the solution. But if it's like sugar, and sugar doesn't really dissolve, but water surrounds it and it's hydrated, okay, we get a solution that doesn't conduct electricity. Or if I put hydrogen peroxide in water, it doesn't conduct electricity. It decomposes into water and oxygen, but it doesn't conduct electricity. That's called a non-electrolyte. And we have varying scales on the electrolyte side. Some electrolytes are very strong and some are weak. So what does it mean to be strong or weak? If you look at this, you can actually put a battery in a circuit and put two pieces of metal into a solution. If it lights up a bulb or makes a beeper sound, you've got electricity going through the water. So ethanol won't separate. It doesn't have a positive and negative side. It doesn't separate into ions. I won't get any light. Potassium chloride is a really strong ionic compound. When it hits water, it separates right into positive ions and negative ions. It will conduct electricity very strongly. So salt water. Okay? Acetic acid. Acetic acid is a weak acid, which means sometimes the hydrogen comes off of it and most of the time it stays with it. So I have some positive ions running around there with some negative ions, but not very many. So I get a very weak light. So that's a weak electrolyte. So if it will dissociate completely, it's a strong electrolyte. If it does not dissociate completely or dissociates just a small amount, we call it a weak electrolyte. Okay? Now there's some examples here of strong, weak, and non-electrolytes. And if you look at them, the strong electrolytes are like this side and that side. I'm going to have a positive and negative. Okay? The weak electrolytes, these are ones that are covalent, but will either gain a hydrogen or lose a hydrogen sometimes. So like NH3, ammonia. Sometimes it'll gain a hydrogen and we'll get ammonium. And then when it does that, that leaves the OH of the water as the negative ion. Okay? And the one next to it is ethanoic acid. Ethanoic acid will sometimes lose that hydrogen at the very end. That's why they wrote it that way. Organic chemistry is a little bit different than inorganic, which we're learning. And that'll give me a positive and negative. Hydrofluoric, same thing. Sometimes that hydrogen leaves, but most often it doesn't. Why? Because fluorine's so strong and it really holds on to it. Okay, so, and the non-electrolytes are usually organic molecules that are just hanging out here. They don't have a positive or negative side. Okay, going forward. This is where we get to a new word. Probably not very many of you have heard of it. It is equivalents. Equivalents are the number of mole of a charge of an ion. So basically, if we look down here at the examples, 1 mole of Na plus is going to be 1 equivalent of Na plus. 1 mole of calcium plus 2 is going to be 2 moles of calcium, or 2 equivalents. 1 mole of phosphate, which is a -3, is 3 equivalents. So it basically just is telling me how many I need of something to balance something else out. That's what an equivalent is. Okay, you got to be able to balance the total positive and negative charge. So it's sort of another way of saying how to put things together. We're going to go on to that one right now. Okay, so this is just some examples you can look at. Let's look at an example of what you have to do. That's after this. So I'm going to play this. Over here on the side, on the right-hand side, you've got equivalent weight. And equivalent weight is basically just the molar mass divided by the number of ions per mole. It could be hydrogen ions, it could be whatever. To get an equivalent, you take the mass of the compound given divided by the equivalent weight to get that equivalent. So let's see if it'll play. I had some problems last time with my, yeah, it's going to do the same thing. Let me bring it up while you're copying that down. Have to use a different browser. It's being dumb. Come on back.
I went to Wikipedia and I decided to pick up the definition for an equivalent there, and I actually didn't find it too useful, but there are some things that I wanted to point out. So it says the equivalent is formally defined as the amount of a substance which will either react or supply with 1 mole of hydrogen ions in an acid-base reaction, or do the same with 1 mole of electrons in a redox reaction. So all I've really figured out so far, I was a little confused when I read this, but I figured out what they're saying is that an equivalent is basically some amount, some number, right? So let's start there. So when someone says, hey, how many equivalents do you have? I know that they're talking about some number. So equivalent is equal to, and this is for some ion, right? So for some ion of my choosing, an equivalent equals some number, and usually that number is in terms of moles. So some number of moles that I need, so needed, to balance something. So I'm actually balancing some charge. So balance the charge of an oppositely charged, so an opposite charge, opposite monovalent. Actually, I should even add balance charge of, I guess I can add it without erasing, charge of 1 mole. That's actually really important, of an oppositely charged monovalent. Okay, so let's jump into an example, because I think that will clear up any confusion that you may have to this point. So let's say we're talking about, for some ion, let's say we pick potassium. Okay, here's our potassium, and I've got to balance out 1 mole of an oppositely charged monovalent. So this is my little line demarking the other side. So on the other side, let's say we have chloride, and chloride is oppositely charged. It's negative, right? And it's a monovalent. It's not -2 or -3. It's just -1, right? So we've got, let's say, a mole of these, because the definition I wrote up just said that I needed a mole of an oppositely charged, and as I'm writing this up, I'm realizing, and I hope you are too, that there's no way in the world I can write up a mole of this stuff. There's no way, right? So let me just get the point across, that just imagine that there are a total of this many, 6.02 times 10 to the 23rd chlorides, because that's really the question. How many potassiums do you need to balance out the charge from all of those chlorides? And that's too big a number to write out in any easy way other than to say, well, maybe you need some number of moles of potassium. And that's why I wrote that right into the definition. So let's figure this out. So we know that potassium binds 1-to-1 with chloride, right? We know that's what happens. So when potassium's floating around and it's going to bump into chloride, it's going to go 1-to-1. So we know that for 1 chloride, we're going to get 1 potassium. And so that means that for 1 mole of chlorides, we're going to get 1 mole of potassiums bound to them, right? And that's going to balance out the charge perfectly. So if someone says, well, how many equivalents do you have for potassium? That seems like a very simple answer. Well, you say, okay, well, one equivalent would then be 1 mole of potassium. Or you could even rephrase it. You could say, well, 1 mole of potassium, and this is how people usually use the phrase. They say, well, 1 mole of potassium equals 1 equivalent. So I know that's the same thing flipped around, but that's how people usually state it. So now let's do a slightly more challenging example, and you'll see where this becomes a little different. So instead of potassium, let me jump into another one. Let's do calcium. So here's a +2. And same thing as before, I'm going to have to choose some oppositely charged monovalent.
Along a little bit, so you can sort of see he's doing the same kind of thing.
And make.
So he's doing the same kind of thing, and he's going to say you need
because
2 of them to
the
1.
chlorides are only one
I'm going to
negative.
rush it along a little bit more because he's a little bit slow doing it, I think. So here
And
he
so then
says
one
you need a
equivalent,
half of
going back to our
a
definition,
calcium
equals
for every 1 chlorine.
1/2 mole of calcium.
It is pretty simple.
And
so if you go even farther, I think he does one more with nitrogen. And you can see that how many would you need of this one? What would be the answer here? Yeah, it would just be, there would be 3, for every 1 hydrogen there's 1/3 of a nitrogen, so 1/3 of a mole of nitrogen is equal to 1 mole of hydrogen. Therefore 1 equivalent is equal to 1/3 of nitrogen. Or
you can
1 mole
very
of nitrogen
clearly see
is
the
equal
pattern
to
that's
3
emerging. So you can see that
equivalents.
anytime
Okay.
you look at
Is there anybody that's
uh,
having problems with this? Everybody get this? Okay, we're going to close this down.
that's what equivalents mean in terms of the mole.
Okay, so we're going to go forward. Whoa, I really went forward. So here is an example where we're going to write it out ourselves. It's all right, just quickly put it somewhere else so you have an example. As we read this, to me, there's going to be a point where they do extra work that I don't think you need to do. So this is what I would do. First of all, I would pull this out. I'm going to write all over this so I can show you what I would do, and then I'll show you how the professor wants you to see it, but you don't have to see it that way. Does that make sense? Okay, so this is what I would do. I pull out everything I need. And the first thing I noticed was what? That this is in liters and that's in milliliters. So they need to be in the same unit. Well, which one's easier to change at this point? You could do either, but the easiest one to change for me is the 800 milliliters, right? So if I take that and I times it by 1 liter divided by 1,000 milliliters, milliliters will cancel, and I'll end up with 0.800 liters. Everybody okay with that? Then I say, you know what? I want milliequivalents. Milliequivalents is right here. I just need to get rid of that liter on the bottom. Well, if I take milliequivalents divided by liters and times it by something that's liters, the liters are going to cancel out, right? So I'm going to put that 154 milliequivalents, going to times it by my 0.800 liters. Liters cancel, and I've got my answer, right? Not too hard. So here, and this is the thing you want to remember on the test, look at the units that you pull out. Make sure the units are the same so they'll cancel, and then just do what you need to cancel those units. So it's just a factor label. just like we did at first. So if I get a recipe that's in metric and I want to do it in English, I've got to convert it. You're converting it. Okay? Very simple and straightforward. That's how I like to look at it. Now I'm going to show you how they want you to look at it. Don't have to. You can still keep it doing it this way. Okay? They want you to say, okay, what are the possible ones you want to use? What things could you use to make it work? Well, if you want milliequivalent, you can't use this one, because milliequivalent has to be on top. If you want to get rid of liters, liters has to be on top, so you can't use this one. And then you set up the whole thing in one big thing. You can choose which way you do it. Doesn't matter, you're going to get the same answer. I think it is. For me, it has been. So this one, I don't like to have to worry about the fractions. I just look and say, okay, what do I have? What do I need to get rid of? What do we need to go to? Done. So if we go back, again, I saw liters and milliliters. Get them both in the same unit. Then how can I get rid of those liters on the bottom? Oh, well, I can times it by liters, and that leaves me with what I want. Okay, so however it works for you, we're going to go forward. Good rule of thumb, remember like dissolves like. So if it's polar, if it's ionic, water will dissolve it. So we have a polar bear there drowning in water. Polar, is getting dissolved. The brown bear is insoluble in water, okay, because it's representing the covalently bound. So like dissolves like. Polar or ionic will dissolve in water because it's polar. Okay? Then we look at the next one here. This is an exception to the rule, and you need to know this exception to the rule. Remember last unit or last chapter we learned about hydrogen bonding. Hydrogen bonding had to do with nitrogen, oxygen, or fluorine directly connected to a hydrogen. Okay? Well, in an organic molecule, you can't have a fluorine directly connected to a hydrogen because fluorine can only make one bond. And if I want fluorine directly connected to a hydrogen, that's the only bond it can make. But oxygen makes 2 bonds, and nitrogen makes 3 bonds. So if I have an oxygen that can hydrogen bond with water that's directly connected to a hydrogen, then I'm going to have hydrogen bonding, and it's going to dissolve. But this only works for small, neutral, organic molecules, usually 3 or less. Half a second. Okay. All right, so you got to remember oxygen and nitrogen with a hydrogen bonding. That will make it soluble. Okay? All right, going forward. Which one of these would dissolve in water? Take a minute. Circle ones you think would dissolve in water. Okay, Jason, I'm going to put you on the spot. Go circle the ones on the board that you think will dissolve in water. And it's okay if you get it wrong. We'll go over him. He's being brave for us.
So sorry.
Carly?
What is it?
It's a candygram. That's it? Okay. All right, let's go through and talk about these. And it's okay if you got them wrong, okay? All right, so remember that water is polar, right? Because I can cut it. And this side is slightly negative and this side is slightly positive, right? So I want something that is polar or that it's ionic, that can be pulled apart. If I look at nitrogen, remember nitrogen has this ghost or unshared pair of electrons, and that pulls it out of the plane. So nitrogen actually can be cut away from the hydrogens. So this one is polar because it has a negative side and a positive side. So this one will dissolve. What about the boron trichloride? No, the problem here is the boron doesn't have that unshared pair of electrons, so it stays in a plane, and it's sort of like one of those little fidget fidget spinners, okay, where the boron is the center of the fidget spinner and the chlorine's on the outside. There's no way I can cut the center away from the parts, okay? So this one is no. That one does not. He circled carbon tetrachloride. What do you think? Is that one polar or nonpolar? That one's nonpolar because I can't cut that chlorine around. I can't cut that carbon away from the chlorines. So this one is a no. Okay, what about the next one? Sulfur dioxide. Okay, this one you got to actually draw out because if you look at just SO2, you'll think, oh, there's an oxygen on this side, oxygen on this side. That can't cut the sulfur away. But again, we have an unshared pair of electrons, and because of that, it pulls the sulfur into a bent position, and we can cut it, so this one is a yes.
So is that one that's circled and crossed out with that?
This one's not, so this one's a not. Okay? What about the next one? So I should circle the ones in blue that are. Yes? Yes. What about this last one? That one is a yes. It's the same reason as this because it's bent. It has two unshared pairs of electrons, so it's going to have a negative side and a positive side, so this one is yes. Okay? All right, so you need to be able to look at any molecule you're given and say, is there a negative and positive side, or will it dissolve in water? Okay? All right, going forward. When we talk about nonpolar molecules, they will be dissolved by nonpolar solvents. So if I take octane, it can dissolve in carbon tetrachloride. Now, carbon tetrachloride is very carcinogenic, so we don't use it as much as we used to, but they used to use it to help clean parts, airplane parts, anything like that. They also used, now I can't think of it, carbon tetrachloride? No, yeah, it was carbon tetrachloride, but there was also a carbon trichloride they used. Okay, so nonpolar. Well, here is showing iodine dissolved in carbon tetrachloride, and it becomes a beautiful purple liquid. But when you're trying to dissolve it in water, most of the iodine stays down here, but you still see that a little bit of iodine is in the liquid because it's got an off yellow color that water usually doesn't have. We've got ethylene glycol here. Ethylene glycol is antifreeze. It does have a little bit of a dipole, so it will dissolve a little bit in water. But oil won't, right? So we've got to look at what's going on there, what's happening, what's going on. So, summary. This is a summary page. Like dissolves like means polar compounds will dissolve in polar solvents, and nonpolar compounds will dissolve in nonpolar substances. So when we say oil and water don't mix, that's because oil is nonpolar or covalent, or another word is molecular, and water is polar. Okay? All right, so let's look at these situations. You tell me what's going on. Determine if they're miscible or immiscible. Now, if you watch the Nearpod, what does that mean? So which one forms a solution, miscible or immiscible? Miscible. I think of it like this. Miscible means mixable. And immiscible, anytime you put im in front of it, means not. So like impossible means not possible. So immiscible would be not mixable. Okay, so let's listen to these ones. 25 milliliters of cooking oil and 25 milliliters of vinegar result in the mixture is cloudy and slowly separates. Miscible, thumbs up. Immiscible, thumbs down. Yep, immiscible. Okay, 25 milliliters of rubbing alcohol and 25 milliliters of water. The resulting mixture is clear and colorless. Miscible or immiscible? Miscible, good. 25 milliliters of chloroform and 1 gram of roofing tar. The resulting mixture is clear but dark brown in color. Miscible. It's miscible. A resulting mixture is clear but dark brown in color. So that's like the milk and the water. If you did the thing back in the back, that was miscible. It mixed. It didn't leave anything solid out at the end. It didn't separate. Okay? So you got to be careful with that. All right, let's go forward. Now, this solvation is basically, does this remind you of anything like this? If I do that?
No.
That we just learned about? What was it?
It was the product of
Activation curve, right. So we have a solute and a solvent. They're in different places. You can see them here. It takes different amount of energies to separate them so that they can combine in our activated complex and end up in a solution. Some things give off heat. This would give off heat, so it would be exothermic, right? Okay. So we can have an exothermic solvation, or we can have an endothermic solvation. And endothermic just means it's the solution ends up higher. Okay? So this should, in your mind, remind you of the activation curve. But it is a little bit different, but it's the same type of stuff. Okay? All right, now we've got something fancy. This is where I had that purple thing out that you could sort of do your lines with, because it's a lot easier for me when I have a grid. If I have something that's a different color, I can put next to it. So this is what's something like what you see on the ACT. And they would ask, what is happening here? Tell me the trends. Tell me what's going on here. What can you get from this graph? What does it tell you?
the temperature is increasing.
Okay, so what?
As the temperature increases, the grams also increase.
So? I'm gonna so what? So what? What would I use this graph for? What is this graph trying to tell me?
The state of solubility that the solutions are at different temperatures.
Okay, that's getting there. Anybody want to add on to that? Look at the y-axis. What is it labeled? Grams what?
Oh, for 100 grams of water.
So how much I can dissolve in 100 grams of water. So how much solute can I dissolve in 100 grams of water at a specific temperature, right? Okay, so let's go and find out. So what do you think this line represents, like a KCl line right here? What do you think that KCl line represents as it goes across? What does it mean if I'm above that line, or what does it mean if I'm below that line? What does it mean when I'm on that line? What do you think they mean? What does the line show me?
Showing you how much of the KCl is dissolved in 100 grams of water.
Right, so what if I'm above that line on the graph? What does that mean?
That
Means
means
I've got more than will dissolve. So if I try and put that much in at that temperature, I'm going to have a solid down at the bottom,
what's that called?
right? And if I'm below that line, what does it mean? I can dissolve more in, right? So let's do this. A, go up 55, go across, go up to 35. You tell me. Where are you? Above the line, on the line, below the line? What's happening? For the A. Okay, you're above the line. So what does that tell you? Helper, what does it mean when you're above the line?
You're at solid.
I'm going to have some solid down at the bottom. Not all of it's going to dissolve, right?
What's it called when you have too much?
We'll get to that in just. So I'm saturated, plus I've got some left over at the bottom. So I've got a saturated solution because things are down at the bottom that aren't dissolving. Okay, what about B? Look at B. So you're going across here at 30 grams, and we're going to the gray line. And where are we going to the gray line at? 50? So what does that tell me?
It's perfect.
Saturated. I'm saturated, but I don't have any extra, right? So there's not going to be any solid left over. Okay, what about C? We're looking with the bright blue line. Ooh, that's the only line that doesn't do what the rest do. What does that tell me about that compound? I've got saturated and I've got some solid, but what does that tell me about that compound solvation? Is it endo or exothermic? It's exo because the solubility goes down as the temperature goes up. So it's forcing the reaction the other way. Good. Okay, what about the last one? 82 grams of NaOH. You're looking at the black line at the top at 10 degrees.
Barely solid. Barely.
Barely what? Okay, a little bit of solid left down at the bottom. Okay, so you need to be able to look at a graph like this and be able to pull stuff off like that. Okay, do I have solid left over? Do I not have solid left over? Am I right at saturation? Do you remember this video where they talked about solubilities? If you don't, and you don't remember that, please get that down real quick. Nitrates, by the way, are NO3 minus. I'm going to write that. Some of them were a little hard to read. NO3 minus. This has a minus on it. This is SO4 with a -2. Is there any others you can't read? I think the rest are pretty. So these were a way that we remembered our solubility rules. We did this when we did our predict the precipitation reaction, but we're going to be using them now again. But we're also not just going to say they're soluble or non-soluble. Everything is soluble to a point. And these ones are so soluble that we can put a lot of stuff in before it starts falling out. Okay? So nitrates, acetates, group 1 metals, always soluble. Remember, group 1 metals does not include hydrogen. Ammonia, always soluble. And then we get to our exceptions. We've got Castrobare, which is calcium, strontium, barium, which are not soluble with the sulfates. And then we've got PMS, which is lead +2, mercury +2, and silver +1, that are not soluble with sulfates or group 17 metals. So remembering this or having this on my 3x5 card might be a very good thing, so that I can see if a solution is soluble or not. If you need to go back and re-listen to that video, it is up on YouTube. Solubility tricks, almost always soluble. If you'll put that or Castrobare with that or PMS, it'll bring this video right up. Okay? I've lost it several times and been able to find it really fast on YouTube by doing that. Okay, we good? Going forward. That's the end. That's where I wanted to get to today. Now, if you have not done the little lab, I'm going to go back with you in just a minute to do the little lab. If you have done the little lab, then I want you to be working on the pre-lab. So in order to be working on the pre-lab, I need to give you some information. So if you will take, and on the back, somewhere on a piece of paper, on the back there's a little bit of a blank space on your notes on the very back page. We're going to just talk about, remember I told you you need a few things that we haven't talked about in lecture to do your pre-lab. So if you put it on the very, very back there with the answers, you'll do good. There is two things that we really need to talk about. It is molarity, which is a capital M. And the way I remember this is it's like a mountain because it's a capital M. And it is moles over liters. And it is moles of solute over liters of solvent. Okay? You're asked to find the amount of grams that you need to weigh out to make a certain solution at a certain amount. By the way, in your lab, it says 100, you need to make 100 milliliters up. We actually need to make up 250 milliliters. So we need to change anywhere it says 100, it needs to be 250. Okay? We don't have enough 100 milliliter volumetric flasks, and you're going to need more anyway. Okay? So we're going to rearrange this equation, and you're actually going to be going moles are equal to molarity times liters. That will give you moles. Once you've got moles, you're going to do this. Remember this? 1 mole of whatever you got, how many grams, and you're going to end up with grams. So you'll be able to weigh it out. Okay? The other one that everybody gets confused with molarity is molality. And it is an italicized cursive-looking M. Okay, and it is moles of solute divided by kilograms of solution. Now, we're not going to know the kilograms of solution, but we're going to assume that we have 250 milliliters. So we're going to assume it's going to be close to 250 kilograms. We're going to be off a little bit, but we need to know how much to weigh out. Okay, so we're going to rearrange this one again and go for moles are going to be equal to molality times liters, or sorry, times kilograms. And that will give us moles again. And we're going to do 1 mole, and we'll do grams, and we'll end up with grams that we can weigh out. Once we weigh out the grams, and we put the water and the grams together, we're going to weigh the solution, and then we'll be able to find the total molality of the solution. But that will get us close to what we want for molality. Okay? Now, the other thing that we need to talk about is, everybody got this down?
What is that box?
Mole. That's mole. And this should be mole right here. Okay, once you've got that done, it'll ask you about I. Okay, so we're going to talk about I just for a second. Like I said, we're going to go into these more. We'll have more examples later, but I'm giving you this so you can do your pre-lab. Okay, so I. This is known as the Van Hoff factor. And basically, all that is, for instance, if I have NaCl, I know it's going to break down into Na plus and Cl minus. So the I for this is 2. If I look at Na3PO4, I know this is going to break down into 3 Na pluses and 1 PO4, 3 minus. So my I here is 4. What am I doing? I'm finding out how many particles it's breaking into. That's what the Van Hoff factor says. So basically I'm saying here I'm going to have an Na plus, an Na plus, an Na plus, and a PO4, 3 minus. So I have 1, 2, 3, 4 particles. If I have something like C2H6, this is a nonpolar molecule. It does not break down into ions. So the I here, 1. So if I had C6H12O6, what would be the I? 1, because that's a organic molecule, and it's nonpolar. It'll be 1. So what about MgSO4? Okay, right, because it would break down to Mg 2 plus and SO4 2 minus, 1, 2, I is 2. Okay? A number of particles you have. So what if I had NCl3? Right, because we have a nitrogen with a 3 minus, and we'll have a chlorine, and a chlorine with a minus. So I have I of 4. What? An organic molecule, usually like SiO2 is one of them, because that's sand. You need to remember that's sand. Okay, always remember this is sand, and it doesn't like to separate. So this I is 1. Anything that has a CH5OH, that would be I of 1. Usually anything that has a carbon, whatever, silicon, whatever, it's going to be an I of 1. Okay? All right. So those of you that have not finished that mini lab, I'm going to take you back in the back. Those of you who have, please work on your pre-lab. Work on getting the other little activity finished and uploaded. That's going to be worth 5 points to you. I'm going to put it into labs randomly. So, okay? Any questions? All right. Let's go back. Those of you that need to go back, let's make sure we grab glasses, because we have broken some things.